Hello and welcome back to Calculus 2 section 6.5, length of the curve. So when we want to measure length of the curve, you just straighten it and then you put the measuring tape and you say whatever the length is and you're done. Now what happens if you can't make it straight? We can still compute in some cases, and then when it becomes third-dimensional, then we go to calculus 3 and then do something else to calculate the length of the curve. So this is going to be calculating length of the curve in 2D, so on xy plane, where that curve is a function that we can work with. So how does this work? First of all, you have some kind of a curve which is represented by a function, and you want to know its length from A to, say, B and so on. Well, what we are going to do is we are going to look at the small part of that curve and imagine that this part of this curve is very, very thin, which is delta x thin, which means that the drop over here is going to be delta y. Now, if I am to draw this much larger, it will look like this. You will have your delta x, you will have your delta y, and the actual length of the curve would be the arch, where this piece over here is the one that you can compute using Pythagorean theorem. So call that, I don't know, little c. So c squared is equal to delta x squared plus delta y squared, because those are the lengths of the triangle. You have the right angle, right, in the corner, so on. So now, because these two are very close in length, we know that by making delta x smaller, letting certain things go to infinity and so on, we get the exact length. So what I can do is I can solve this little piece c as the square root of delta x squared plus delta y squared. And then with a little bit of magic, I'm going to take delta x squared common factor and kick it in front of the square root. So when I take delta x squared common factor, I'm left with 1 plus delta y squared over delta x squared, right? Because I have to put that down there. Now delta x squared goes outside as delta x, and we are left with this 1 plus delta y over delta x, everything squared. So this is the length of the single piece. And then what we do is we add infinitely many of those, which means it earns that sum in front, and then that turns, when you set it to infinity, you got yourself an integral there. So the length of the curve must be integral from a to b, square root of 1 plus the derivative squared dx. So this is your formula for length of the curve. Now in honors classes you must know how to derive it, which is the proof on the right side, derivation. In this class, obviously, you have to memorize the formula that calculates the length of the line, which is on the cloud over there. Now we also have the version for y, which will be L is integral c to d, square root of 1 plus f prime squared of y, everything dy. That's just the y version of the formula. So what now? Wait, did I put the stream on? Okay, good. Whew. Now, one thing that you have to be a little bit careful about here is what types of functions we can pick, because you can't integrate everything and anything. So we're going to pick some easy stuff first, and then we're going to learn about one trick, and that's how much we can actually do here. If I put something that has to do with, well, I have a few different problems for your project. Again, it's all application. If it's not possible for you to integrate, well, it's project. You're supposed to use Mathematica or, I don't know, contact your local shaman or something and figure out how to do the integral. But for the most part, for the exam, it's going to be something that you can actually do without aid of the software, something that you can actually integrate. So let's take a look at few examples. I love how on the problems they say use calculus, because clearly you can figure out things differently. So for problem 8, they're giving you y equals 4 minus 3x on -3 to 2. Right, that's the interval on x-axis. So x equals -3 to x equals 2. Now you're looking at this thing and you say, well, I have x values, I can compute y's, and then I have x comma y, I just use distance formula. Yeah, exactly. But then why simply, if we can complicate things, let's do the calculus on this, see how it goes. So we know that the length of the curve is going to be integral from -3 to 2 square root 1 plus the derivative of the whole thing is -3 squared dx. Don't forget to square it. That's where the grade dies. Forget to square it. Also for the disk method, you forget to square it. So integral of -3 to 2, that's a 9, 10, that's a root 10 dx. So what's the integral of root 10? Exactly. Computed from -3 to 2, which is 2 root 10 plus 3 root 10 is 5 root 10 units, whatever. So 5 root 10, if you are to do the distance formula between the 2 points, you have to get the same answer. So remember how I actually went and made the argument that the formula that you guys saw for the disk method was actually 3D because it's a volume formula? Well, I have to do the same thing here because this is length. Length is one-dimensional. Don't we compute areas with integrals? Right? So it's kind of counterintuitive to actually have this for the one-dimensional entity. But it's actually true. Look at this. If you just forget a little bit about this 1 plus over here, square root and square are opposites of each other, and you have integral of a derivative. You see that? So they all canceled out. The only thing that's left behind is just f of x. So it's one-dimensional. This formula is one-dimensional. Again, square root and square gone, and then derivative kills the integral. So just if you drop this 1 plus, all of that stuff cancels out immediately, and you have just f of x, which is one-dimensional thing. So in general, in a nutshell, right, this is one-dimensional. So it does represent length of the line, which is what we need, right, for the length. Okay. Problem number 12. And that's where the Actually, lecture ends and class ends, because there's nothing else past this one formula for the length of the curve. You know what the concept is, you know what the length of the curve means. I don't have to explain any of that stuff. I just memorize the formula and start using the stuff. So the function y for problem 12 is 3 ln x minus x squared over 24 on interval 1 to 6. I hope this is going to work. We know that we need derivative to plug in, and we'll have to square it later. So what's the derivative y prime? Are we good on the derivative? So derivative of x squared is 2x, and then you cancel for 12. It's always fun. What's the derivative? Yes, it is. Yes, good, good. So now we immediately plug everything in the formula. I have 1 plus, and then over here I have 3 over x minus x over 12 squared dx. So all we need is to integrate this, and we're done. Well, what's the only thing that we can actually do here? What is the only thing that I can do now? Yeah, square it. So let's do that. One plus square the first one. That's going to be 9 over x squared. Then you have the middle term, which is going to be 1/2. You all see it's 1/2? It's going to be 3x over 12x doubled, so 6x over 12x, which is x and x cancel, 6 over 12, 1/2. Middle term is 2ab. So just, or you FOIL on the side, whatever. And then you have plus x squared over 144. Maybe I should, I don't need these parentheses, but I'll put them there just because I can, all right? I'm not really wasting ink. So now what happens? What was the only thing that I can do? What can I do? Do what? Plug in. What do you mean plug in? What's the only thing that I can do now? 1 minus 1/2. How much is that? All right. So I have 9 over x squared plus 1/2 plus x squared over 144. Where's my dx? Oh my god, I lost the point. Yeah. You'll be putting this plus x and plus c's and you know, dx's, otherwise -1. So it's either plus c or -1, whatever. All right. Now I need you all to stare at the board, because this is going to blow your mind. Look at this. If this, with this negative on the middle term, came from expansion of that guy, then this, with the middle term positive, which is everything is the same, identical other than that middle sign, has to compress into what? 3 over x plus x over 12, everything squared. And now it's under the square root, and this is how the square root dies, and you can integrate. Yep. Yeah, stare at this, because this is the only way you do it. All right? And the next section, same problem. So this is 90% of the chance that it's going to be your exam question or final exam question. And then you have 10% chance the previous one. So one more time, you expand this and you realize that this line and this line are now the same, apart from the sign of the middle term. If this expansion is from there, then that expansion has to go into that one. Now, square and square root annihilate each other. All you have to integrate is a joke, and you move along. So integral 1 over 6 of 3 over x plus x over 12 dx. What do we get? X 3 ln absolute x plus exactly from 1 to 6, and we have a number on the other end. How awesome is this, huh? Like just this trick is about $400 of your tuition for this class. Yes.
That last step is the same as what we started. That's 3 ln x. I mean, and then the absolute value in the thing.
The only thing you have to do is get rid of the 1.
And all the change was the sign change in the absolute value.
When you do enough problems, stuff will be clearer. Yes?
So, because you're saying that the whole next section will be some questions.
The next section looks exactly the same, except over here in this formula that we put on the cloud, there will be an f of x in front of this one to calculate the surface revolution of this thing, and there will be 2 pi in front. So you will be calculating the area so you can paint or give people to do design and so on. So what I said is the next section, which is 6 surface area revolution, is going to have the same calculation in terms of compressing it with a plus half minus half square till square root. So it will have same trick. I call that the trick.
So so what we just did with it all turned into 3 ln of absolute value plus x squared plus 4. That like if we get to the point where we see, like on a test, if we have that question and we get to the point where we see, oh, I can just use that trick, and we just jump directly past doing it with that work.
I hope it will.
Like I mean, like for grading purposes, what you
Just do enough homework problems so you see enough variety of it. Okay, bye stream.